Hello everyone, happy to see you here. Welcome back to my channel. Today we have very interesting and I would say like funny algebra question. We have 1 to the x equal to 6. And a lot of students may be thinking this is like not possible. 1 to the x cannot be equal to 6 because, for example, when we apply natural log on both sides, so let's do this right now. When we apply natural log on the left side, so we have natural log of 1 to the x, and we're gonna apply it on the right side, so natural log of 6, then this x will come down right here because this is like the main log property. As a result, we have x times natural log 1 equal to natural log 6, and the last thing we're gonna do, we're gonna divide both sides by this natural log 1. So we need to find our x, yeah? So we're gonna divide both sides by natural log 1. And when we do this, we can easily see the really interesting expression. So we have x equal to natural log 6 right here, and divided by natural log 1. We can easily find natural log 6. This is like our constant. We can easily do that with our calculator. But what about natural log 1? Natural log 1 is equal to 0. So a lot of students might be thinking, right here we don't have real number roots, and this is a correct approach, correct method. We can't find our real number root. This is not possible in terms of real numbers. But right now I'm going to show you a really great approach in terms of complex numbers. So I think everyone know about Euler's identity. This identity looks like that. So we have e to the power I times theta equal to cosine theta, and plus I sine theta. So right now I'm going to consider it as a complex value. So this is our Euler's identity, and we really need it because right now in this moment we can say that right here we don't have real number roots, and right here we have a complex unit. So right now let's consider this Euler's identity, and let's try to solve this question in terms of this Euler's identity. Let's prove this identity real quick. Everything is great. So theta equal to 0. Let's check it. Let's see what will happen when we're gonna plug in theta equal to 0. So as a result, we have e to the power I times 0 equal to cosine 0 and plus I times sine 0. Sine 0 equal to 0 right here, and cosine 0 equal to, right here we have 1, and I times to the power e to the power I times 0 gonna be equal to 1. So as a result, we have 1 equal to 1. So everything is great. So this identity works perfectly. But what I'm gonna do right now I'm gonna find real quick substitution. So let's do this. Let our theta equal to 2k pi. So I'm talking about integer k. So k is our from the z, yeah, equal to 1, 2, 3. So this is my substitution, and let's see what will happen when I'm gonna plug in, instead of this theta, when I'm gonna plug in this 2k pi. Let's see what will happen. As a result, what do we have? Our identity gonna looks like that. So as a result, we have e to the power I times 2k pi, yeah, 2k pi equal to cosine 2k pi. Instead of theta, we're gonna plug in right here. Instead of theta, we're gonna plug in our substitution. So this is our substitution. So as a result, we have cosine 2k pi and plus I sine 2k pi. Okay, this is my substitution. And right now the very tricky moment, because right now I'm gonna see what will happen when k gonna be equal to 1, 2, and 3, and a result will be really great. So first of all, I'm gonna write for k equal to 1. So let's see what will happen when k is equal to 1. When k is equal to 1, we will have really interesting identity. As a result, we have e to the power I times 2 pi, because k is equal to 1. So we're gonna plug in, instead of k, we're gonna plug in 1. So e to the power I times 2 pi equal to cosine 2 pi, because k equal to 1, as you can see right here. So as a result, we have cosine 2 pi and plus I sine 2 pi. Okay, I sine 2 pi. And of course, we know this value because cosine 2 pi equal to 1. So this expression is equal to 1. And I sine 2 pi, right here, this expression equal to 0. Okay, in terms of periods, sine 2 pi equal to 0. And if we add 1 plus 0, as a result, this expression will be equal to 1. And just keep in mind this 1. Right now, let's see what will happen when k is equal to, so for k is equal to 2. Let's see what will happen when k is equal to 2. So as a result, we have e to the power I times 4 pi equal to cosine 4 pi, yeah, cosine 4 pi, and plus I sine 4 pi. And if you look closely, we have the same period because cosine 4 pi has the same thing with the sine 2 pi is equal to 1, and sine 4 pi has the same thing with the 2 pi. So as a result, we have, it just depends on the period, yeah? But the meaning is absolutely the same, equal to 0. And if we add it, we have 1 plus 0 equal to 1. And just keep in mind this one as well. We have 1 right here, 1 right here. And let's see what will happen with the one more step. Let's see what will happen when, for example, k is equal to 3. Let's do this like a sequence. So 1, 2, 3, and let's see what will happen when k is equal to 3. As a result, we have e to the power I times 6 pi. Yeah, everything we plug in right here in this identity with our substitution, okay? Equal to cosine 6 pi, sine 6 pi, and plus I times sine 6 pi, okay? 6 pi. And if you look closely, the same thing with the period. We have sine 4 pi, sine 6 pi. We have absolutely the same thing. We have 0 and cosine 6 pi equal to 1. So 1 plus 0 equal to 1. And as you can see right here, according to this property, according to this substitution, if we have a sequence of integers, we have 1, 2, 3, with this substitution, with this theta equal to 2k pi, when we plug in, instead of k, when we plug in 1, 2, 3, 4, so when we plug in integers, every time on the right side we have 1. And this is absolutely the same thing with the k equal to 4, for example, okay? When k equal to 4, I don't want to check it real quick, but when k is going to be equal to 4, k equal to 4, we will have 8 pi, 8 pi, and 8 pi. So we will have 1 and plus 0 equal to 1. So we will have absolutely the same one on the right side. And why this information is really helpful for us. So this expression right here, this expression on the left side, is all the time equal to 1 when k is equal to 1, 2, 3, 4. When k is integer, every time this expression is equal to 1. So what I mean from these 4 steps. So this expression on the left side, so then, let's write it right here. So then, this expression e to the power I 2k pi, e to the power I times 2k pi, all the time equal to 1, we proved it right here, equal to 1 when k is our integer. So when k is z, we are talking about like k equal to 1, 2, 3, and a lot of these values. So we will have like a period 8 pi, 10 pi, 20 pi, 100 pi, 1000 pi, and doesn't matter about this period because we have all the time 1 on the right side. So it can be a really huge period. In terms of like our trigonometry thing, we will have absolutely the same thing on the right side. So we're gonna have 1. And right now, why this 1 is extremely important for us? Because in the beginning, what we had in the beginning, 1 to the x equal to 6. And we already proved that right here we don't have real number roots. So we proved it, we eliminated our real number roots. So right here, no real roots. And then I write this Euler's identity. And in terms of this Euler identity, we can easily change this one by this e to the power I 2k pi. So in the beginning, we had 1 to the x equal to 6. This is our question from the beginning. And we know that we don't have real number roots. So right now, instead of this one right here, let's plug in this e to the power I 2k pi. Okay, let's do this right now. So as a result, we have e to the power I times 2k pi raised to the power x, because we plug in it instead of this one, raised to the power x, is equal to not 1 but 6. So instead of this one from the beginning, I plug in this expression because this expression is equal to 1 when k is integer. Right now, let's simplify this expression a little bit. First of all, we're gonna apply a natural log on both sides, or before it, we can easily multiply our powers. So as a result, we have e to the power I times 2k pi times x equal to 6. And right now, let's apply natural log on both sides. So natural log e to the power I 2k pi x right here. So we can easily apply natural log and natural log on the right side, natural log of 6. And right now, this power will come down right here because of natural log property. As a result, we have I 2k pi times x times natural log e equal to natural log 6. What we're gonna do next, of course, natural log e, we can easily cancel it, equal to 1. And right here, we're gonna divide both sides by I 2k pi, because we need to find only our x. So we need to divide both sides by I 2k pi. And we're gonna divide it on the right side, I 2k pi. So from here, we're gonna cancel it real quick. We will have only our x on the left side, x equal to, and right here we have natural log 6 divided by I to k pi, and the final thing, of course, we can multiply both sides, our numerator and denominator, by I, because we don't need this I right here. So as a result, we have I in our numerator, I in our denominator. So we're gonna have like I square in our denominator. So we have x equal to, we have I times natural log 6 divided by I square times 2k pi. And of course, I square equal to -1. This is our imaginary unit. So our x is going to be equal to minus I natural log 6 over 2k pi. And of course, we need to mention that our k is integer. So we're not talking about real number. We don't know what will happen when k going to be like real number value. We know everything about k integer. So k is our integer value, and k 1, 2, 3, we're talking about these cases. So when k is integer, this is our answer to our question. And as you can see, we know pi, we know natural log 6, we know k is our integer, and then x is going to be a solution to our question. So let's write our final answer to this question. Of course, this is not like a full solution to this question, because we don't know what will happen when k is like a real number root with a real number value. We don't know anything about it. So let's write our final answer. So x is equal to minus I natural log 6 over 2k pi. And of course, don't forget about these two lines. K is integer, so this is extremely important part, because we don't know anything about k. When, for example, k gonna be like a real number root, we don't know any information about it. When k is integer, this is a solution to our question. This is a funny question. I really want to share with you this solution. I really hope you enjoy it. If you have a question, if you have your answer, your approach, you can also write a question down into the comment section. I really hope you enjoy it. Maybe a lot of students don't like this type of question, because this looks like not a good question in terms of school, because we prefer real number root. We don't need this like complicated thing with the complex values. And of course, we need to know it. I really hope you enjoy it. I really hope you learn something new. And once more, a solution to this question. So thank you everyone for your time. You can also write your notes, write your response down into the comment section, and see you in the next videos. Have a great day and take care of yourself.